Sorry, we suddenly went dark there, and all you missed was the signal. So we've now counted the number of valence electrons. We've identified the central atom in the cases that there is a central atom, methane, phosphorus trichloride, and nitrate ion, and carbon dioxide, and we formed a single bond to each of the outer atoms. In only one of the cases, the case of methane, have we actually used up all of the valence electrons in the course of doing that, right? We've used 8 electrons here to each of these pairs. So this is a complete Lewis structure for methane. Normally, we would actually indicate its three-dimensional structure, though, by showing the carbon atom and the 2 hydrogen atoms that are in the plane of the board with regular straight lines. But then we would use a solid wedge to indicate the hydrogen that's coming out of the board, and a dashed wedge to indicate the hydrogen is going back. This is 4 electron groups on the carbon, right, 4 hydrogens, each equivalent that it will be a tetrahedral molecule with an angle of 109.5 degrees for each of the hydrogen, and the 4 hydrogens at the corners of the tetrahedron. So the solid wedge represents coming out in front of the board with page, and the dash wedge represents going back behind. So that's a complete structure for methane, and we're done. Right? We've used all 8 electrons. There are no additional electrons to be used. But in every other case, we use less than the total number of electrons in the course of building our molecules. So we're going to have to need to go on to step 4 in the drawing of Lewis structures. And step 4 is to use the remaining electrons by filling the octets on each of the outer atoms. Generally, the outer atoms, obviously, are the more electronegative of the bunch, and it would make sense that you would want to put additional electrons on most electronegative elements first. That's actually going to continue to be true in the case where you have outer atoms that are not all the same. In our case, all of our atoms are all the same, or 2 oxygens of carbon dioxide, 3 fluorines of phosphorus trichloride, 3 oxygens of nitrate ion, but that's not always the case. And if it is the case that they're different, put them on more electronegative element first. In the case of hydrogen fluoride, hydrogen already has its duet. There's really nowhere else to put the other electrons other than fluorine. We've used 2 in the bond. We have 6 remaining. And that will fill the octet on fluorine. And we now have a complete and correct Lewis structure for hydrogen fluoride. 8 electrons on fluorine, 2 electrons on hydrogen. Pretty simple. In the case of the phosphorus trichloride, we used up 6 electrons. We have 20 remaining. And we're going to put 6 on each chlorine for the octets. So we've used up an additional 18, but we still have 2 more. Those 2, because there's no more room on the outer elements, are going to have to go in the central atom. And at step 5, if there are still electrons remaining, place them lone pairs on the central atom. So we will put that last pair of electrons on phosphorus. And we now have a filled octet on each chlorine, and we have a filled octet on phosphorus, so that is now a complete and correct Lewis structure for phosphorus trichloride. But one of those electron groups is a lone pair. So instead of taking a tetrahedral molecular geometry, we'll take a trigonal pyramidal electron geometry. We'll put the lone pair at the top, and chlorine here, and then we will show the one chlorine coming out, and the other chlorine going back, and one lone pair with 3 atoms. For carbon dioxide, right, we've used 4 in our bonds. That leaves us with 12 remaining. And we will put them on 2 oxygens. That is a complete Lewis structure, but it is not yet the best Lewis structure because the carbon atom still has an unfilled octet. And we'll come back and deal with that problem shortly. Get rid of ECl3, since we're done with that one. In the case of the nitrate ion, we've got 18 left. And we will again fill the octet on each of the nitrogen or oxygen atoms or electronegative. And that will use up the 18 electrons. And you'll notice in these 2 cases, for instance, there's a multiple of 8, 24 here, 16 there are no electrons left, so there are no electrons to be put on the central atom. Here, we use 2, and we have 8 electrons remaining. We'll put 6 of them around the oxygen because oxygen are left, and this is not a multiple of 8. We'll end up with a pair of electrons with a carbon as well. In all 3 of these cases, we still have an element that doesn't have a filled octet. So we still don't have a completely, we're going to have to do something about that. So we're going to move on to step 6, which is if the central atom is left without a filled octet, we're going to make multiple bonds by moving a lone pair from one of the outer atoms in to make a bonding pair to make a pi orbital. When you do this, that you make that second bond, that multiple bond, from one of the outer atoms into a bonding pair, and not just by adding another pair of electrons, because if we just make a multiple bond here by adding a pair of electrons, then we no longer have the right number of electrons. And if you don't have the right number of valence electrons, everything's wrong. Right? So we need to make sure that we move a pair of electrons rather than forming another bond with a pair of electrons that didn't exist. So we're going to take a pair of electrons away from this oxygen and make a pi bond. So we now have a carbon-oxygen double bond. Here, that same oxygen, and make a triple bond over here. Also take a pair of electrons from the second oxygen and make a double bond. That's more pleasing because it's more symmetrical, and it's also better for reasons that will become clear shortly. Doesn't really matter which oxygen we choose. All 3 of these oxygens are equivalent, and we just need to move one bond from the oxygen to the nitrogen, so that is now a legitimate Lewis structure. It's not done yet, but electrons off the oxygen. We don't actually have the choice now of taking the pair of electrons off the carbon. If we were to take this pair of electrons off the carbon and form a bond there, we you would end up with 10 total electrons. Cannot expand its octet to have 10 electrons around it. No second row element can expand the octet. So we're going to have to take the other pair of electrons from the oxygen. And now we have a filled octet on each atom. So those are all legitimate Lewis structures now. And the carbon dioxide Lewis structure is in fact finished, except that we need to explain why the correct Lewis structure for carbon dioxide has double bonds on both sides, rather than having a triple bond on one side and a single bond on the other side. Other than it's symmetrical, that's pleasing, that's okay, but it's not a great argument. So we need to move on to the last step. One you shouldn't forget, which is to assign formal charge, assuming there is any formal charge. The formal charge is a bookkeeping system that allows us to compare the number of electrons the atom has on it now to the number of electrons that it brought with it as valence electrons, as to its name. And from that, we're going to subtract the number of valence electrons. So 7A, count the number of electrons the atom has. 7B, right, subtract from that the number of valence electrons, the number of electrons it brought with it. When the atoms bond, each of them is going to take half of the electrons that it's bonding. So the number of electrons the atom will take with it if the molecule breaks up is all of the lone pairs. It's not sharing those. It signed no agreement, right? Those are in its own bank account. It's not a joint bank account. But it only takes half of the bonding electrons. That's a joint bank account, and when the marriage breaks up, each of them takes half of the electrons that are in that bond. So for this oxygen, for example, we would count the number of electrons it has to its name. That's these two lone pair electrons, which I abbreviate with LPE. And there are 6 bonding electrons. So it's taking 1/2 of those bonding pair electrons. Right. 6, so it's taking 3, and the total then is 5. So it has 5 electrons to its name, but its valence was 6. So it has 6 valence electrons. It actually doesn't have as many valence electrons, or it doesn't have as many electrons. So it's actually 6, not particularly happy. Right? It's going to have a +1 formal charge, and we usually circle the formal charge. That's not an actual charge. That oxygen is actually partially negative because it's more electronegative than the carbon, which means that it has a greater tendency to pull electron density towards itself. It's going to pull a dipole that looks like this. But formally, since it only has 5 electrons and it brought 6 electrons with it, it's not very happy. It has a +1 formal charge. Carbon's happy, right? Carbon has 4 electrons to its name, half of the 4 bonds. Valence is 4, life is good, there's no formal charge on carbon. This oxygen has 7. This oxygen has, to its name, 7 electrons. 6 lone pair electrons, plus half of the 2 bonding pair electrons. And so it's got 7. Valence was 6. has actually got an extra electron. That's a formal -1 charge. The charge correct, you would actually flip this around. You would take the number of valence electrons and subtract the number of electrons it has to its name. Right? So in this case, we would take the number of valence electrons, 6, and we'd subtract the number of electrons it has to its name, 5, and we'd end up with 6 minus 5, or plus 1. In this case, we would take the number of valence electrons of 6 and subtract the number of electrons it has to its name. Valence 6 electrons minus ohm is minus 7 minus 1. Formal charge is minus 1. So it might be easier to do it that way. I generally compare the number of electrons it has to the number of electrons it should have, and then determine whether it's short an electron, in which case the charge is positive, or whether it's got too many electrons, in which case the charge is negative. But valence electrons minus owned electrons is going to give you the proper sign on your charge. So there's formal charge separation in this molecule with a triple bond to one oxygen and a single bond to the other oxygen. Possible Lewis structure for carbon dioxide that has a double bond on each side. Both of the oxygens own, right? Number of owned electrons is 4 lone pair electrons. Lost half of 4 non-nuclear electrons, which is 2. So 6 electrons owned, valence of 6, no formal charge. Carbon's happy, 4 owned electrons, right? 4 valence, happy, no formal charge. If there's a choice, you generally want to minimize the amount of formal charge separation. If it's not possible to eliminate the formal charges, which it won't always be, and you want to try to put the minus charge on the more electronegative of the two forms. Those are kind of corollaries that you can think of as 7C and 7D. Right? Once we've decided whether or not we have to, once we've assigned the formal charge, and we're deciding between two possible structures, we want to look to minimize the formal charge, which is what we're doing here. That molecule is better because there's no formal charge. And if we have a choice, we want this oxygen here, right, owns 7. It had a valence of 6. 6 minus 7, minus 1 formal charge. Oxygen will always have a minus 1 formal charge on it if it has 3 lone pairs and only 1 bond, right? Because in that case, it will always own all 6 of the lone pair electrons and 1 of the bonding pair electrons. So this oxygen over here also is a formal charge of minus 1. That oxygen's happy because it has 6 electrons to its name, and it came with 6. The nitrogen here had a valence of 5. But now it only actually owns 4 electrons. 5 minus 4 is 1. That nitrogen has a plus 1 formal charge. Anytime nitrogen has 4 bonds to it, 4 of those bonding electrons when it splits the bond. You'll notice that the net charge has to add up to the overall charge on the atom or ion, molecule or ion. In this case, since the ion is overall minus 1, 2 negative formal charges and 1 positive formal charge adds up to that minus 1. Right? That's essential. Otherwise, it's screwed up. You have the wrong number of electrons. There are 2 equivalent structures that we could draw for that. because all three of those oxygens are identical, and those are referred to as resonance structures. And for resonance structures, we show the double-headed arrow. And we can put the double bond to either of the other two oxygens and come up with equivalent fluid structures. So there are three equally contributing resonance structures to the nitrate ion, each of which has a double bond to one of the oxygens and a single bond to the other two. Two oxygens that are singly bonded have -1 formal charges on it. The nitrogen in all three cases has a positive formal charge on it. If we wanted to represent that with a single structure, we could use what we call a resonance bracket. We have a -1 overall charge on it. We would have a single bond to each oxygen. Each oxygen would definitely have a lone pair, two lone pairs, because in all three structures. And then we would represent the additional electron with a dashed line. So those three dashed lines represent the other bond, whichever one of those oxygens has a -1 charge, whichever one of those oxygens is doubly bonded, and it also represents the additional two lone pairs that would be on the other two electrons. So we've got 6 additional electrons represented by these dashed lines. Sometimes there's a bond there, sometimes there's a lone oxygens. We can say that the bond order here is 1.33. It's 1 1/3. Right? Because we have 4 bonds, 1 bond here, 2 bonds there, 1 bond there. We have 4 bonds divided between 3 structures. So this would be 4/3. If we want to think of what the charge on each of those oxygens would be, there's a minus charge here and there's a minus charge there. So there's 2 negative charges shared each of those oxygens effectively has a -2/3 charge. And in all 3 structures, right? So the resonance hybrid is sometimes, and in that case you don't really have a choice, you have to show all the resonance structures. So let's take a look at carbon monoxide. Carbon monoxide is an exception to the general rule that says that we want to put the formal minus charge on the more electronegative element. Because in the case of carbon monoxide, the only way to fill the octet on both atoms is in fact to end up with a negative formal charge on carbon and a formal positive charge on oxygen. That's the opposite from the way the charge is actually distributed. There's really a partial negative charge on oxygen, the more electronegative element, and a partial positive charge on the carbon. But remember, formal charges are bookkeeping, they're for Lewis structures, they have nothing to do with actual charges. How did we get those formal charges? These two and half of those 6 have electron, but its valence was only 4. 4 minus 5 is -1. Oxygen owns the same as carbon, right? Owns the lone pair and half of the 6 bonding electrons, so it owns 5, but its valence was 6. 6 minus 5 charge. It's 1 electron short. It brought 6 electrons, but it only gets to take away 5, so it's got 1 too few, which means it has a positive charge. Carbon brought only 4 electrons, but it takes away 5. It's got 1 too many. It has a negative form of charge. Carbon is kind of a bad house guest in this case. It brought 4 beers to the party and drank 5. We don't invite it back. Oxygen, right? Always invite oxygen. And that concludes the second